Well, good afternoon, everyone. It's a pleasure to express a warm welcome on such a bitterly cold day to Dr. Jin-Shan Wang, founder, chairman, and CEO of First Advanced Materials Inc. In Nanjing, China. Welcome, Dr. Wang. Now, Dr. Wang obtained his PhD degree in polymer chemistry from the University of Liege, Belgium, in 1993. I suppose that means we can ask you questions in French.
You may.
Go. His work involved the development of ligated anionic living polymerization technology for methacrylates, leading to a number of industrial products which were commercialized by Gulf Aquitaine. Later, working at Carnegie Mellon University as a postdoctoral research associate, he discovered atom radical polymerization, ATRP, now a fundamental polymerization technique for polymer synthesis and design. From 1995 on, Dr. Wang's research has focused on the development and commercialization of polymers and nanomaterials. He worked for Eastman Kodak down the road in Rochester from 1997 to 2008, where he contributed to the development of lighting extraction materials for OLED displays, as well as well-defined polymers for imaging applications and optical nanocomposites with high refractive index for LCDs. Now, his talk today will focus on the current status and future perspectives of OLED lighting, with an emphasis on the challenges and developments in light extraction technologies and OLED lighting panel commercialization. Please welcome Dr. Jin-Shan Wang.
Thank you. Thank you very much. Good afternoon, everyone. Thank you very much for your very kind welcome today. Actually, I had a very good day here, and also very, very warm introduction. And today, as the startup company executives, so I just talk about something which we started the business in China, the OLED lighting, and mostly from application and also industrial point of view. And today, I would like to talk about the OLED and OLED lighting, and then why we need OLED lighting, and some progresses over the last many years, and the issues and the challenges still remain, and then give you some kind of outlook for this kind of new lighting sources and also new field. And if we have time, I'd like to describe a little bit to you about the first OLED and the first advanced material, two companies I actually started in China. And if I still have time, I'd like to introduce a little bit about the ATRP. But that's an older story, but still, for students, maybe some kind of a useful insights into that. And this organic OLED actually was discovered, and especially the device using such kind of new stuff was discovered at Kodak, actually many years ago in 1970s actually. And actually it published a couple years later when people really came to Kodak to try to license that technology. And the principle is like that. People might know this. If we put the current, the electron and the holes meet together in the light-emitting layer, then to excite the organic materials to generate different kind of lights based on different materials you use. So today, actually, if people here, we have cell phone, the Galaxy from Samsung, that's OLED based. Instead of iPhone from Apple, which is LCD based, that's two different technology actually platforms. And also, if from RGB, the light mixture together with very right compositions, so you may get the white. That's today we use that as a lighting source. And if you see display and lighting, basically they are the same base, same technology. However, they still are different because for display, you need to have the very fine patterning pixels with each have different colors. And for lighting, just is a one big pixel. And so because of so many very fine pixels for display, so you need a very good technique to pattern it. And also many steps involved in order to have such kind of very well-defined displays. So it's very large investment involved. Typically, you need $10 billion, something like that, even more than $10 billion. Or even like in China, so many now people try to do that. It's more than probably $30 billion for one production line. And for OLED lighting, it's quite less complicated than display because you don't need really TFT to drive pixel, right? So involve less step, and you don't need that much money, and probably 10 times less compared to display. So that's the reason why I will show you so many companies start with, OLED lighting, including the one I founded because we don't need that much money to start a new business. And for display and OLED lighting, actually they have different requirements. Not necessarily OLED lighting is in terms of technology is quite simple, not necessarily it's less challenge. For example, for lighting, actually you need to have very good white color. That's not so easy to obtain. And of course, you need to have a higher power efficiency in order to be useful for lighting. So today I will focus on basically that part. And that's 2013, actually now the OLED not only scientifically up to very high degree, and technology-wise advanced so much thanks to two giant companies from Korea. One is Samsung, another one is LG Display and LG Chemicals. And this is already on the market. This is 50 inches OLED TVs, curved, and very high resolution. And for the lighting part is a little bit behind the display because it started late and also faced more challenges from application or the industrial point, for the application and the market point of view. And still people already come to start to make lighting products. And why already lighting? So we have so many lighting sources already, right? The very recent one is LED lighting. So why already lighting? So mostly from an energy point of view. So here you see this table actually in something like 15 years, actually China will become the country consuming the most of the energy compared to other countries in the world. Second, compared to today, China will consume double. So that for China, such kind of developing countries, really is very important to find new sources to have to create the new sources of the energy. And people looking to different kind of things, right? That's we have so many people actually work on like photovoltaic cells, solar cell energy. Actually, from application or from industrial or from practical point of view, that's still only consists very small fraction of the all energy we created today. Here, like in 2010, it's 1 year production from photovoltaic cells only can supply Beijing for 8 days. So this is cannot depend on actually for one nation's energy policy cannot focus on depending on some kind of new energy technology in order to meet today's challenge and the requirements. If it's well known, actually, I don't know if you know that lighting represents one sector consumes the most electricity today. Like in China, such a kind of developing country is about 15% of consumption of the energy, electricity actually is by lighting. But for the developing countries like the United States, Canada, and Europe, it's about 20%. So here you have a calculation, like in 2010 in China, the consumption on lighting is about 15%. If we save 10% of that, and by increasing some kind of power efficiency of the lighting sources, so actually equal 40 times of the energy generation by photovoltaic cells. So that's really so important, not only to generate the new energy, on the other hand, it's very important to save the energy from consumptions. So that's where lighting come to the play, and that's the reason why the OLED lighting come to, like LED, come to become important today. If you compare it to different kinds of lighting sources, you will find that actually this is very old lighting bulbs, and this is a CFL lighting tube, and LEDs are mostly actually they are 0.9 sources. Because of 0.9 sources, so people needed to put the lighting bulb inside of something, need a fixture to do that. That's first is to reduce glare, right? In order to distribute the light, diffuse the light. However, if we put the fixtures here, there are two things that happen. One is reduce efficacy. So if people think about LED is 160 lumen per watt as lighting sources, however, as a luminaire, the efficacy only is about 70 to 30% of that. It means it's less than 100 lumen per watt. So because you put it into the fixture. And at the same time, because you use fixture to distribute the light, so the cost will increase. Actually, today we know that. We are going to buy a lighting bulb is very cheap, right? However, if you buy a luminaire, it's very expensive. So that's the reason why. So, and on the other hand, and the OLED is a planar, it's air lighting sources. So mostly, you don't need to reduce glare. So basically, you don't need a fixture to do the job as other lighting sources. And in this case, lighting panel are almost as the lighting source the same as luminaires. So in this case, so the use of that kind of lighting source is very more efficient. And of course, in terms of the fixture part, you don't need to add that cost. Even you have to pay more money to buy the lighting panels. So here, basically, it's a very unique feature for OLED lighting or OLED lighting. And on the other hand, for the energy saving, so it means OLED, the efficacy actually is as higher as LEDs based on the calculation. So it could be achieved to more than 200 lumen per watt. Actually, this could be more than 10 times more efficient compared to today's lighting bulbs. And some other advantages of OLED lighting, like for the LED, because it's very small size, and it's around 1 square millimeter. So with that kind of size, there's so much energy on that, so the temperature increases significantly when you put the current into it. So that's the reason why for LED, we have to use large heat release kind of fixtures like aluminum metal here. And for OLED, actually you don't need. So it's the air lighting. You don't generate, basically no much heat generated during the process. And people could use that actually as it is. And the second part actually is the operation current density for OLED is very low. The third, the light outcoupling is getting easier because the organic material, even the refractive index is as high as 1.6. However, compared to the inorganic materials, actually is more than 2, so easier to get the light out from the device. Another advantage of OLED lighting, so people can basically use different kind of substrates to make the device. One is transparent, so you could have a light pass through two sides, top and down. And another one, actually people can use plastics as a substrate, so you have flexible lighting panel. So that's the reason why nowadays there are so much activities going on, especially sponsored and supported by government. And in the United States and Canada, not too much, because probably here the gasoline prices is still so low compared to the rest of the world, because here the energy is not, probably is not a big issue compared to, less significant compared to in China or even in Europe. As you see here, actually Europe quite a big program over there, and also Japan is so many companies involved in OLED lighting. Of course, in China we have a few, and also government. Actually, there are so many different programs involved in OLED lighting research and development. Like in China, we have 5 years program, and in USA there is a called a multi-year plan. As Europe is very significant. Europe put a lot of money. With whole Europe, there is one OLED 100 EU, and there are also more than 30 different small programs sponsored by different kind of organizations. And Korea very aggressive because they really like to have OLED lighting by 2027, 100%. But that's very aggressive plan, but I'm not sure if they can get that. And Japan, solid state lighting by 2030, here including LED and OLEDs for Japan. So as you see that the OLED lighting is so important, from energy saving point of view. And so that's the reason why actually the government support a lot of programs all over the world. And over the last many years, actually, people have made quite a bit, very great progress in that area. So here I'd like to talk a little bit more about that. First, very important because that's a kind of energy saving lighting, new lighting sources. So the very important stuff, first you have to higher power efficiency, means higher efficiency. Here we can see, here actually the efficiency, there are 3 different factors that contribute to that. The first one is structure, device structure, that's very important. Of course, combined with that is the material. And the third one is a light extraction. I will talk to you a little bit later about what's exactly about the light extraction. And the structure, of course, that's a kind of discovered and by Pan and Naraniel at Kodak as well. Change from one stack to multi-stacks. So change that kind of structure actually from one stack to tandem OLED structure to have a couple of very important impacts on today's OLED technologies. The first one is reduce electronic shorts. Because the OLED materials and layers very thin. Total is about 200 nanometers between 2 glasses, the substrates and the cover. So if there is any kind of small particles here, will make that device short. so it won't work, such as the dust or some kind of ITO sparks or even metal from the anode. So if we use multi-actual tandem structure, could reduce such kind of a short and basically make the device work better. Second, and the current efficiency will become higher, and which is actually proportional to the number of the units. Here you can see here two tables, two plots, and we can see that, and with 3 tandem structure hybrid, and actually people can get higher current efficiency. At the same time, improve the power efficiency as well. And actually can make the device last longer. So the structure, so today's standard structure basically for industrial nowadays for OLED lighting products, mostly based on tandem structure. The second important progress, technology-wise and scientifically also, and is light extraction. As we know that the light generated from organic materials actually, because the refractive index of organic material is higher than 1.6 or even higher some materials. So when it passes through the glass, and from the glass to the air, there are 2 times total internal reflection. The light, actually only 20% of the light generated from the organic materials could reach to the people's eyes because of the total internal reflection. So the light either trapped inside of the device or just came out from the side of the device. So really people don't see that. So that's the reason why very important, in order to increase the power efficiency, really important that you have to, we call it extract light from the device. So there are 2 ways actually to do that job. One is put light extraction, or called extraction enhancement layer structure outside of device. After fabricated the device, so we put the extraction layers on top of the glass. And the second one is put extraction layers actually between the organic materials and the ITOs. So this we call it is external, that we call it internal. So external, you only can extract the light which is trapped inside of the glass. And here you can extract the light from whole device. So that's the reason why internal extraction layers is more efficient than external extraction layers. And this is not new story. That's many years ago, for many years, and people proposed different kind of structures and fabricate different kind of structural materials to do that. However, even it's good in the lab, and also it's good on the paper, but it's difficult to fabricate with larger production, right? Such a kind of structure, it's not so easy. And even you can produce that, but that's so expensive. People still like the lighting board today we use. We don't like to buy this one, right? And on the other hand, there is one drawback about this well-defined structure, because that will make light directional. It's not well diffused, from the device. Will have some kind of angle dependence. So that's the reason why at the Kodak, with Dr. Tian, we came out with the idea, just it's a kind of a scattering light extraction. Use some kind of scattering microparticles, and which can randomly scatter light. So have both benefits. The first one can get the light out. Second, the light out randomly, so you don't have angular dependence. Actually, here you can see here is no any extraction structure. This one with external means just put the scattering layer on top of the glass. Here is put the extraction layers between the organic materials and the ITOs. So, and that's this kind of structure actually made by at first OLED represent the highest efficiency today people can make today, and using such kind of structure with which is external. Now we can get about 74 lumen per watt, and the corner is very right. It's a little bit, towards higher corner temperature, but still within that quarter. So it means it's quite a wide corner. And with IES, which is more difficult to make, because think about it, you have to make light extraction layer inside of the device. It's very difficult. And however, in the lab, we still can make such kind of structure, and with efficiency as high as 112, which is the highest nowadays in the world. That's a world record. And the color also is very right, just on the black boundary line. So it's very right, white color, which is very difficult. So many people reported we can make very high efficiency OLED lighting panels, but so many lighting panels, they don't generate white color. The color sometimes so often like here. And actually nowadays with reported devices which within this code area, only probably not more than 10 or 5 companies who can make that. The third very important factor is lifetime. Because the luminaires of OLED is so expensive, right? So you don't like to just use that as lighting bulb. Lighting bulb is only a couple thousand hours, right? 2,000 hours lifetime. Because it's cheap, so you can change it easily. But for this one, really we need it as long as possible. Because if we change all this, it's very expensive. It's not just a lighting bulb. And the two factors actually, it's two kind of life time which we have to focus on, and actually affected by different kind of reasons. The first one is the shelf life. Because OLED device is very sensitive to the water and oxygen. That's we know for this kind of device. And within time, so often there is a dark spot generated inside of the device, which basically will damage the whole device. So this is really important. It's a kind of encapsulation technique is so important here. So, and the desiccant also. So inside of the device, you have to have a very good desiccant. And depending on which kind of applications, if we like to use top emitting lighting panel, so you have to use transparent desiccant and also transparent anode. And also the edge seal usually use that to do encapsulation. So we need to have very high quality in order to meet such kind of requirements. And the second one is operating life. Mostly because organic materials, very difficult for organic materials compared to inorganic materials is they always degrade, right? The material degradation. So that's so material is very important in that regard. Nowadays, actually, that not achieved too much over the last years because people really not focus on the lifetime, because lifetime here is already around 100,000 hours, or even with T50 at 2,000 Canadian per square meter, more than 40 or 20,000 hours, already very good for 1 or 2 years for people to use that. So still here we believe there is some room here to improve. So another very important progress, before 2013, mostly people make the 19 panels in the NAP. So in the NAP to make a 19 panel is not difficult because you don't need to make that much first, and you don't need a NAST for the panel. You don't need that NAST to know. You just show up. That's enough, right? But if you like to make the products, you really need to be cheap and also at the same time have a very good quality. So that's the reason why the manufacture process is very important to come to make that into the production. And in 2012, actually, the LG Chemical came with the first linear production line to make OLED lighting panel. Usually, OLED lighting panel consists of about 20 or even more than 20 layers. So you have to have, each step is one layer. So you have to have, I suppose we have more than 50 meters long, the production evaporation the system. And in order to evaporate each layer by each layers along the line. So this is the world second, actually, linear, we call it Gen 2. It means the size is about 370 times 470 millimeters, the substrate, the production line. And LG Chemicals had the first one, and the first OLED had the second one. And this one actually was built in for more than 1 year and started to production summer in August, actually, last year. So, and the last progress over last couple of years, especially last year, people really try to find the applications for such very expensive lighting panels. Because if no such kind of applications, it's hard to justify how to do the business and how to push that forward. As you have seen that, actually nowadays, many companies are doing that kind of work because they need to find the application, otherwise they don't have the sense to do that. The first one actually is from Osram, and they already put that into the Audi, the car, as the backlight, so the red one. And this is from first OLED. Actually, it's Nanjing University Scientific Park, a sign of that park. So put each one is a lighting action panel. It's about 50 times 100 millimeters. And another one, actually, lighting panel is from LG Chemicals. And the Luminaire is made by Acuity brand. That's the largest luminaires producer in the world, actually, which is now located in San Francisco. And this one actually, it's a kind of a touch with a. And another one, this is a table light from Philips, and it's beautiful, but I don't think the direction will go that direction for the OLED because they use quite very expensive light fixture, so that actually will add more cost to the lighting products. Anyway, that's they show really have some kind of to make some new luminaires. So we already talked about the progress over last 5 to 10 years, and I know here mostly is technology advance, not much scientific advance here because that's so practical. You see what I mean? It's a kind of so, and however, each progress represents very difficult challenge to the people, especially take the technology from the NAP small device like that big when we made actually 3 years ago to that big today. So it's a lot of technology challenges, and also we have to solve a lot of issues over there. And still, for OLED lighting, compared to OLED display, people are not so optimistic nowadays because there are so many issues still involved in OLED lightings. The first one, basically now OLED and LED are both solid state lighting. They compete nowadays very strongly in the diffuse area. It means because OLED lighting is a kind of diffusing lighting sources. It's a air lighting source. So the LED basically nowadays also want to occupy such market. As you know that market represents 74% of total lighting market. So that's a huge market. If LED cannot succeed in that market, so no big business for LED. Just as a decoration light is not enough. And so that's the reason why over the last 2 years, the LED industries put a lot of efforts get into the diffuse area. And for LED, basically, as we know that, I don't know if here Samsung or LG came out with LED TV. Actually, it's not a LED TV. It's still LCD TV, only use LED as backlight. The principle is the same. To use that backlight as lighting products for general use. So basically, you have kind of LED here. You have the light guide plate. So to diffuse the point light from LED to generate the planar light. And for OLED, as we have already seen that, in terms of efficacy, in terms of lifetime, and which you can catch up, that's no problem. And however, the cost is really significant for OLED compared to LED. Because as we know that here, most of the people to fabricate the electronic device. So that needs a lot of money to do that, right? Compared to LED, just take the LED package, then put some kind of light guide plate, then you can become very good planar light sources. So here is planar LEDs. That's product from GE recently, and which you see here. And basically, it's using LED lighting board, then plus the light guide plate to diffuse the light, and which can reach quite a good efficacy. This is 3 times compared to the incandescent lighting bulb, or it's 2 times compared to CFL. And also, that's another one. So this is quite not that expensive as well. So that's where if already we have to compete with that, then the cost will become a very significant issue. And so if you look at this chart in terms of different kind of requirements, here are 2 actually left for OLED to really is very important. One is we have to have a low cost, because this kind of product is daily life product. You cannot be that expensive. For display, people may pay a little bit premier to buy a very good display. Even you buy a iPhone, pay like a couple $100. So people will pay that. But if you say pay $100 buy a lighting bulb, lighting panel, no, people don't want to do that, right? So here is the cost. This is, as I said here. And the efficiency actually here is, this is the product. And in the lab actually is already here. So that's the reason why they put kind of dash also here. So others already match the LEDs. So no big problem. So here nowadays the low cost is really a big issue. And actually this is applied issue. And back to academic, this is also a scientific issue, right? Could be. So that's when the cost reduction is become very important. So for Korea, European, and the US already set the cost, the targets is around $10 per candle luminaire, and or $100 per square meters of the lighting panel. And Europe are also similar to that. But problem is that, I said this against the LED, the problem is that United States, the Department of Energy set the target every year, but we always put the date back each year as well. So it's not so easy to achieve that. And the second, for LED now, they meet the target actually faster than people thought. So each year. So there are two things, two solid state lighting sources compete with each other. Personally, I'm not so optimistic by OLED lighting if we use glass-based, the lighting panel. So we have to change a lot of strategy and also even technology platform over there. So here is the cost of comparison from Yoni, and you can see here today is about 70 times more expensive if we buy a OLED lighting panel compared to LED with the same efficiency, and even by 2020 it's still 16 times. So still we need to either find a very niche applications or we have to reduce the cost. So that's things let's see how we can get there. So the expensive, because we have so many steps in order to make lighting panel. Actually, the materials nowadays is expensive. If we have larger production, the material, if we have volume, the material is not expensive, and because we only use very small amount. So really, is the process actually is more expensive. And here, Konica actually came out nowadays in the lab with the single stack the structure, and they can get very good color and also get very high power efficiency, as high as 81 lumen per watt. So that's one. And the second, so nowadays technology all based, first is on the glass as a substrate. Second, use the evaporate the technology, right? The small molecular, then you evaporate it. And people try for a long time and to use solution process to do that. However, you have so many layers, solution process will be a problem because the integrity of each layer is harder to keep. Or if you want to keep, you have to add a lot of other technology in there. So that will add more cost. So that's also from Sumitomo Chemicals. Actually, they actually can use solution process to make lighting panels already achieved to some kind of degree, but that's one direction. But still not there yet. And GE and DuPont have spent a lot of time to do that kind of same job, but so far not so successful. So that's one thing still needed to work on. In order to do that, so you needed to use, instead of use ITO, you needed to replace ITO. So that's another kind of things come out we have to use other kind of transparent conductive films or materials. So that's the reason why nowadays come out with nanowires compared to other kind of stuff. Nanowires or metal mesh are two very promising candidates to be used as transparent conductive materials to replace ITOs. Actually, there is, people already put transparent conductive films, try to put into the market these years for touch panels. And that's the first step. After that, people can take the same technology into the device. But first, people have to generate the good films in order to achieve the, what. So, personally, I believe if we want to make OLED lighting successful, I suppose flexible is the way to go. Because LED is hard to, people is trying to put LED into the flexible substrate. Some company or some small companies already come out with some kind of things, but still for OLED is more adapt to that kind of technology than LEDs, because this is as we see here, people started to make such a kind of things, and in that sense, actually, as I learned this morning, talked to many very great faculties in this institute. Actually, people here, this is a very hot topic here. I believe that's the way to go for OLED lighting as well. Because the glass-based OLED lighting panels, it's very hard to compete with the plastic-based LED lighting panels, put in this way. And if we go to the flexible OLED lightings, here also we needed to change the philosophy. We have to change the strategy for whole industry. Because if we compete with LED for the general lighting, probably no way to go, even we use flexible OLED lighting. We have to find some kind of applications and which could most benefits from a flexible lighting, not a panel here, like this is the paper or cutting, whatever those, right? And to do that, actually, there are so many technologies or science involved. And as we know that you have to first have a barrier films, right? And because this is very sensitive to water and oxygen. And then we have to have, conductive layers. And to do all those kind of things, you have to develop the coding process or printing process or whatever the process to put all those into the device, right? So here, actually, that's a lot of things involved here. And but I believe OLED lighting, that's probably the best hope to have the OLED lighting to really to become a very big product in the market. That's all for my talk about OLED lighting. So please let me just a couple minutes about two small companies I founded in China. The first one is the first OLED. First OLED now is at least in OLED community is very well known, because in the world that's only the second company to manufacture OLED lighting panel. Philips, Osram, GE, and Panasonic, that's four biggest lighting companies. They only made some samples in the lab. So they never put that into the production. The reason we don't know, but I believe because they don't like to interfere their existing business. Mostly like LED, they are in a very good position. The company actually is founded in about 3.5 years ago. Nowadays, we totally invest about 400 million renminbi. And I already said that these two things I already talked about. We got very strong support of the Chinese government. The government put 200 million renminbi over there without asking anything. So it's good for me, but sometimes it's put also very high pressure on myself. So that's the reason why I left by the end of last year. And to do that, why do this? In China, I found that it's when you move up the industry to the up chain, you see in China there are two, especially in the electronic industry, there are two things empty over there. One is material. All material actually came from Japan or Korea or Germany. Second is equipment. So if without these two, it's hard to make cheap panels because you have to buy the materials from outside. You have to buy the equipment from outside. And most of our investment for the production line is the equipment. The equipment costs about 120 million renminbi to have that production line. So if we're not successful in that, so that become actually waste, right? So that's the reason why I like to move that to the up, to the chain, to the up, to the material side. So we are focusing on we just started last year, end of last year, and also strongly supported by the Chinese government because they always also seeing that very important nowadays, focusing on the materials and also related to the functional films. For mostly, we focus on flexible electronics. And also we do something for life science application also. And another thing is together with the government and the investment firms, and actually we try to create a new business model and build incubators inside and outside of China for high-tech startups and also R&Ds. So this is we are still discussing and with government officers and also the people who can put the money into that. So the ATRP, Xiaosong suggested me to talk a little bit about ATRP. And this is what I did, feel proud of myself in my professional career, in addition to the first OLED I founded. And actually this solved a problem pending in polymerization field, academically and also industrial-wise for more than probably 40 years. So since 1956, Wang discovered living polymerization. Hundreds, probably thousands of people really tried to find the way to have a living radical polymerization. And thanks to Michael George at Xerox, not far from here, he first introduced a stable free radical polymerization to make a first living radical polymerization of styrene. And however, that's not enough because styrene, it's very narrow, represent very narrow, the in terms of monomers. So people really like to get more monomers involved, more general technology. So that's the reason why at CMU, I conceptualized this ATRP actually a long time before I went to CMU with Professor Matiszewski. When I did my PhD at University of Liege, I started to think about that. When I did my PhD work on living anionic polymerization at that time, because I thought when I read this paper from Professor Quirk, and actually free ions can make living polymerization of metaacrylate, I thought, why not free radicals? Because usually free ions, you cannot make living polymerization of anything because too reactive. However, they put such a kind of kinetic equilibrium between dominant species and the reactive species to control the livingness of the polymerization, so they can make a living polymerization. So that time put that question into a paper, on a paper actually, can we find something here to generate the free radicals and at the same time react with free radicals to make a dominant species. If the reaction is so fast, so basically we can control the polymerization. And at the same time, I read a paper from a very dear, small molecule organic chemists. They have similar group transfer radical addition. And this actually gave me the ideas because they don't like to have polymers. Polymer for them is a failure, right? However, I saw that polymer for them is a failure. Polymer for me is a good thing. So that's the reason why. So we started by just changing the ligand, changing the temperature, changing the monomer structure. So we discovered together with Professor Matuszewski, discovered the atom transfer radical polymerization. And nowadays, with that, you can make almost everything. The paper actually, 3 papers actually, very good citation. And I didn't have time to look at after 2009 because I started my business in China. No more interested in science. So, and actually that time, and the first communication about 2,100 citation. And the second paper is a full paper, is about 1,000. So try to be part of that. And actually I found this, and with that kind of innovations, even I'm not interested in science anymore, but still with such kind of spirit to do the startup company, still, very, very great, very aggressive to push, to get the money from the government. Okay, just a little bit of story here. Thank you very much for your very kind, attention. Any questions?
Well, thanks for a great talk. I'm sure there are lots of questions.
So I was looking at the data you presented on slide 29. This is results with the internal extraction structure.
Right.
I wonder if you could give us a bit more details or just comment at least on how you're obtaining very high efficiencies. I look at the candela. If you want to go back to slide 29.
Wow, that's a key technology. Yeah. I can, here actually it's, yeah, I know. It's still difficult to put into the production. We only can do that in the lab because, if we introduce a little bit dust over there we'll have problem. So here?
Yeah, so I see, 29.
Here?
Slide 29.
Oh, 29, okay. 29.
So I look at the candela per amp, and this is efficiency, and this is 263.
This one?
Is this a tandem device or a single cell?
The tandem. Three units. Right.
The voltage looks very small for a tandem device.
Oh yeah, your voltage is not that high, right?
So can you please comment on how this is all happening?
How we can get there?
How you can get this
Yeah.
efficiency at this
Yeah, without that kind of efficiency, it's already about 50 newton per watt. So basically, that's a structure issue, and also material combination. Dr. Tian is very good at that. He is a color maker, so he can make a very good color with good structure, and a lot of know-how about the material combinations. So already he can make the device with around 50 newton per watt without any kind of extraction. And here with internal, basically, this is the two things are basics. The first one, you need to have the, here, I have to back to here, okay? You need to have, where is mine? Oh, you need to have that particles. This is TiO2 microparticles, and very highly scattering particles. That's the first. Second, the matrix, the index should be as high as possible. And this is difficult, especially to make a larger size panel. But small one is okay, but the larger size is difficult. That's the reason why so far it's still difficult to. And these are two very basic requirements. And of course, there are others. So, such as the layer of the scattering layer should be very smooth. This analysis is hard to make. So yeah, we have found a way to do it. So that's a kind of things probably not, sorry, not to disclose here.
Yes.
Yes.
In some of the experiments that we have done, so we have looked at polymers that were labeled, and they were emitting light, right?
Right.
And sometimes we are able to generate some microdomains by cross-linking, random cross-linking inside the matrix.
Right.
It would scatter, and there would be a lot of more light that would come out of the polymer matrix than I was anticipating, certainly because of the scattering.
Right.
But here what you are doing, so in that case, the microdomains are generated inside the polymer layer that emits.
Right.
But here what you are doing, you are putting the scattering there's a scattering layer which is outside the light-emitting layer.
Right, right.
Is there, so it's outside. What would happen if it was inside? It was scattering the light as it is being generated inside the light-emitting layer.
Or inside of organic materials?
Yeah?
It's hard because how to evaporate, it's hard.
Oh, it's because
Yeah. The nearby layer actually, this organic layer is here just one layer. Actually, it's about 20 layers. Each layer is only about from 10 nanometers, some even few nanometers, to 10 nanometers. It's very small. And the whole organic layer is about 200 nanometers. So if we put this particle is around 500 nanometers, already make everything don't work, right?
But in this case, it's because particles is you have to. Let's say if the organic layer was a polymer that you would cross-link in some space, that would generate domain that would scatter light inside.
No, the organic materials could be. There is one thing also here is very important. You cannot the material cannot absorb the light. You only scatter light, cannot absorb light. So basically, like with aromatic, with other kind of substitutes, not good for such kind of purpose. Even you can scatter light, but at the same time absorb the light.
And the features have to be, you said 500 nanometer because it has to be the same size as the.
No, you don't need it.
Can be smaller?
Here?
The features of the scattering matter you said around 500.
No. Actually, it's a kind of random distribution. It's hard to have like such kind of material with very uniform size. Actually, uniform size is not good. It's not good because if the scattering with directional scattering, it's not good for OLED device because that will generate the angle dependence. So we like to have random scattering particles.
Yes.
So far you come in China and become some supplier for some company like Samsung, LG Chemical?
We are competitor with them.
So think about China, some company like a Hixing company. They also provide like OLED some panels.
China now, you mean China?
Before like Hixing.
Oh, yeah. No company now in the world start to produce OLED panels except Samsung and LG. And even there is one Taiwanese company called AUO. They try to supply but the yield is very low. So they are not so good. Yield is very low because come to the production, if the yield is only 20%, that means not good. you need at least 75 or 85% of the production yield. And but there are 5 Chinese companies with about $100 billion investment, and total together, I mean, they are going to start to produce the OLED panels. It's 4 color. It's not lighting panel, okay? It's OLED display panels this year. One is Huaxing from Shenzhen, another one is Visionox from Suzhou, and another one BOU is in Beijing, and the other 2 Tianma, and also another company, I forgot what's the name of that. Oh, Huhui, that's in Shanghai.
So your company in the future become competitor or supplier of each other within your company?
Look, with my company,
Yeah.
oh, I will supply material to them, so they will become my god.
Well, that's a good point in which we should stop, I think, and thank Dr. Wang for his very keen insights and perceptions of the opportunities and the challenges that lie in LED and OLED devices.
Thank you.
Thank you very much.
Thank you, sir. Thank you.